Beryllium is a fascinating element, often overlooked but incredibly important in a variety of scientific, industrial, and technological contexts. With the atomic number 4 and the chemical symbol B, beryllium is a lightweight steel-gray metal that belongs to the alkaline earth metal group in the periodic table. Despite its relatively low profile in public awareness, beryllium's unique properties make it critical in applications ranging from aerospace engineering to nuclear reactors. Discovered in 1798 by French chemist Louis-Nicolas Vauquelin, beryllium was first isolated in its oxide form from the mineral beryl. Interestingly, beryl is the same mineral that gives us the gemstones emerald and aquamarine. It wasn't until the early 19th century that metallic beryllium was successfully extracted. This process involved reducing beryllium chloride with potassium, and it marked the beginning of a growing interest in the element's physical and chemical characteristics. One of the most striking features of beryllium is its low density. It is one of the lightest of all solid elements that are not gases at room temperature. Despite being light, beryllium is remarkably stiff. Its modulus of elasticity is about 1/3 greater than that of steel. This means that beryllium is highly resistant to deformation, which is why it's often used in structural components where both weight and strength are critical factors. For instance, in the aerospace industry, beryllium is used in the manufacturing of satellite and spacecraft components, where reducing weight without compromising integrity is essential. So, thermal stability is another standout property of beryllium. It actually has a pretty high melting point, about 1,287 degrees Celsius, or 2,349 degrees Fahrenheit. Even under extreme temperatures, beryllium manages to retain its shape and structural properties. This quality makes beryllium ideal for use in environments where heat resistance is really paramount, like in jet engines or even nuclear reactors. When it comes to nuclear applications, beryllium plays a particularly interesting role. It's a good neutron reflector and moderator, which means it can slow down neutrons and reflect them back into a reaction core. That makes it useful in both experimental and power-generating nuclear reactors. Plus, beryllium doesn't easily absorb neutrons, and that further enhances its utility in nuclear physics. For this reason, it is often used in nuclear weapons and as a component in neutron sources for research. Chemically, beryllium is quite reactive, although it resists oxidation in air due to the formation of a thin, protective oxide layer. It reacts with acids and alkalis and forms various useful compounds such as beryllium fluoride and beryllium chloride. Beryllium fluoride is especially notable for its use in specialized molten salt reactors, where it serves as part of the molten salt fuel mixture. From a crystallographic standpoint, beryllium has a hexagonal close-packed structure which contributes to its stiffness and stability. This structure is part of what makes beryllium difficult to work with. It's brittle at room temperature and can fracture under stress, requiring specialized handling during manufacturing processes. Beryllium's interaction with X-rays is another area of interest. It is highly transparent to X-rays, which makes it a valuable material for X-ray windows in analytical equipment. These windows allow X-rays to pass through while protecting the internal components of the device, a balance that is not easy to achieve with most materials. Despite its many uses, beryllium poses significant health risks. Inhalation of beryllium dust or fumes can lead to a chronic and potentially life-threatening condition called chronic beryllium disease, or CBD, which primarily affects the lungs. For this reason, industries that work with beryllium must adhere to strict safety protocols, including air filtration, protective clothing, and regular health screenings for workers. The mining and extraction of beryllium is also, pretty limited because of its relative scarcity and the difficulty of refining it. The primary sources of beryllium are the minerals bertrandite and beryl. The United States is actually one of the few countries that produces significant amounts of beryllium, especially from bertrandite ore mined in Utah. China and Kazakhstan are also notable producers. Because of its strategic importance, especially in defense applications, beryllium is often subject to export controls and regulatory oversight. In the realm of electronics, beryllium is often used in the form of beryllium-copper alloys. These alloys combine the conductivity of copper with the strength and non-sparking quality of beryllium, making them ideal for tools used in hazardous environments like oil rigs or grain silos, where sparks could trigger explosions. Beryllium copper is also used in connectors, switches, and other electrical components due to its excellent electrical and thermal conductivity. The optical properties of beryllium are also worth mentioning. It's used in the production of precision mirrors and optical systems, especially for applications that require both high stiffness and low thermal expansion. Beryllium mirrors can be found in telescopes, including those in space observatories, where even minute deformations can lead to inaccuracies in imaging. The James Webb Space Telescope, for example, uses beryllium in the construction of its primary mirror segments, coated with gold to enhance infrared reflectivity. Though it is not commonly found in consumer products due to cost and safety concerns, beryllium's specialized properties ensure that it remains indispensable in high-performance, high-reliability environments. Looking ahead, the future of beryllium may involve expanded use in fusion energy research. As the world seeks sustainable energy solutions, materials that can withstand the extreme conditions inside fusion reactors are in high demand. Beryllium, with its neutron moderation capabilities and thermal resilience, could play a key role in making fusion a viable energy source. In summary, beryllium is a remarkable element with a unique combination of physical and chemical properties that enable it to perform functions no other material can quite replicate. From aerospace and nuclear science to precision optics and electronics, beryllium quietly underpins some of the most advanced systems in the modern world. However, its toxicity and scarcity require careful management, ensuring that while its contributions are significant, they are always handled with caution and respect.